Friends, a very good evening and welcome to the 7th A P Mitra Memorial Lecture. I am Amitava Sengupta and I shall be the moderator for today's program. Before we begin, may I request all of you, except the speaker for the day, to kindly switch off your cameras and mute your microphones for a smooth conduct of the proceedings. A warm welcome to all of you to our annual A P Mitra Memorial Lecture event in the memory of Dr. Patricia Mitra, one of India's greatest radio scientists. Today is also the World Ozone Day. Every year, we organize this event on this day in recognition of Dr. Mitra's significant contributions in this field. This year, the 7th A P Mitra Memorial Lecture is being organized jointly by the NPL Former Scientists Forum, NPL-FSF, the Indian Radio Science Society, InRaSS, and the CSIR National Physical Laboratory. It will be delivered by Dr. Patricia Doherty, Director and Principal Scientist, Institute for Scientific Research, ISR, at Boston College in Boston, Massachusetts, United States. Dr. Doherty is a world leader in the use of Global Navigation Satellite Systems, GNSS, for ionospheric research, and we are extremely thankful to her for accepting our invitation despite her very busy schedule. Now, to begin our program, I'm glad to inform you that we have always had unstinted support to our organization of this lecture from the family of late Dr. A P Mitra. This time has been no exception. I now invite daughter of late Dr. A P Mitra, Dr. Patricia Mitra, more commonly known as Mila, to pay our respects by garlanding Dr. Mitra's photograph and offering floral tributes. Mila and her spouse, Dr. Krishna, are in the audience and they have shared this video with me that I shall play now. I invite all of you to join us in paying our respects to Dr. Mitra. So let me share my screen and show you the video. Thank you, Mila. May I now request you and Krishna to please turn on your cameras and say a few words if you like.
Good evening, everyone. And on behalf of Dr. A P Mitra's family, I would like to thank our speaker today, Dr. Patricia Doherty, for willing to be here today and grace this occasion and share this lovely webinar today with all of us viewers here. I would also like to thank all the organizers for remembering my father every year on this special day, World Ozone Day, and by inviting so many renowned scientists and speakers, several of whom are here today. So thank you again, and I really appreciate what all of you are doing to keep this spirit alive and keep his memory going with such wonderful webinars every year. Thank you.
Thank you, Mila. Thank you so much. So you may turn off your videos now. I request all of you to please turn off your videos. So next, may I now invite Mr. R.B. Saxena, who is the General Secretary of the NPL Former Scientists Forum, the main organizers of this lecture series, to say a few words about the Former Scientists Forum and the A.P. Mitra Memorial Lectures. Dr. R.B. Saxena.
Thank you, Dr. Sen Gupta ji. Professor Venugopal Achanta, Director NPL, Dr. Patricia Doherty, Director and Principal Scientist, Institute for Scientific Research, Boston College, USA, Dr. S. Anantakrishnan, President, India Radio Science Society,
Sanju.
Dr. Amitabh Sen Gupta, Chairman AP Mitra Memorial Lecture Committee, our forum patrons, Professor Krishnalal ji and Professor Vikram Kumar ji, Shri N.K. Vadva, Joint Secretary, Former Scientists Forum, family members of late Dr. Mitra, NPL Former Scientists Forum colleagues, NPL fraternity, distinguished participants from Indian Radio Science Society and abroad, ladies and gentlemen, on behalf of NPL Former Scientists Forum, I welcome you all to our annual event of AP Mitra Memorial Lecture. This time it is the 7th AP Mitra Memorial Lecture today, which is going to be delivered by Dr. Patricia S. Doherty on Storms from the Sun, the Science of Space Weather. Just to give a background about the NPL Former Scientists Forum, our forum is a professional, social, non-profit organization with well-defined aims and objectives. Like, we look after the interests and welfare of the members in general. We organize scientific lectures, talks, common interest to the members by experts of various fields. And also we organize social activities for the members. Now coming back to AP Mitra Memorial Lecture, the NPL Former Scientists Forum has instituted an annual lecture series in 2014 in memory of one of its very distinguished former patrons, late Dr. A P Mitra, ex-Director NPL and ex-Director General CSIR. This lecture series aims at providing a platform to honor the lifetime contributions of late Dr. A P Mitra, FRS, to radio atmospheric sciences in India and on an international level. These AP Mitra Memorial Lectures held regularly at the CSIR National Physical Laboratory, New Delhi, and have been organized jointly by NPL Former Scientists Forum and National Physical Laboratory. Earlier, 6 AP Mitra Memorial Lectures have been delivered by eminent scientists and researchers in the field of radio atmospheric sciences, which are Professor Govind Sarup, Dr. Krishna Swami Kasuri Rangan, Dr. Shivaji Raha, Professor S. Anantakrishnan, Dr. Archana Bhattacharya, and Dr. Anil Bhardwaj. The 7th AP Mitra Memorial Lecture this time has been organized jointly by NPL Former Scientists Forum, the Indian Radio Science Society, and CSIR-NPL as a webinar. The holding of this AP Mitra annual lecture is proposed to be primarily funded by an endowment created out of contributions from the SY National Organizing Committee for the URSI General Assembly 2005. Also from the late Mrs. Sonda Mitra, wife of late Dr. A.P. Mitra, Dr. Mitra's family, Dr. K.K. Mahajan, and former students and associates of Dr. Mitra. Now we look forward to an enlightening lecture by Dr. Patricia. Thank you. Dr. Sen Gupta ji.
Sorry, I got muted. Sorry.
Yes.
Friends, in our organization of the AP Mitra Memorial Lectures, we have always been fully supported by the CSIR National Physical Laboratory, a place which has been the workplace of Dr. Mitra for close to 5 decades. Before the COVID pandemic period, the APM lectures had traditionally been held at the NPL auditorium. This time too, the director NPL has kindly provided his full support to our organization. He has also kindly agreed to preside over this function. It is now my pleasure to invite Professor Achanta Venugopal, Director CSIR NPL, to say a few words of welcome. So Professor Gopal, if you could kindly turn on your camera and say a few words. Thank you.
Thank you, Dr. Sen Gupta. It's really a privilege to be here. I just would like to say a few words. CSIR-NPL is the National Metrology Institute of India. We have had historically very strong groups in the areas of material science and characterization and radio atmospheric science. Dr. A P Mitra was a pioneer in radio atmospheric science in India, and he has set up the radio science division at NPL. And he rose to the level of Director of CSIR-NPL and Director General of CSIR. Dr. Mitra, in his illustrious career, he has worked on Earth's near space environment, first with ground-based and later with space techniques, including rocket and balloon-borne payloads, as well as MST radar and SROS satellite. His research has continuously evolved, covering contemporary topics, and during his later times, actually, he worked on global environmental changes. He's very well recognized and well decorated scientist with numerous awards. Today is a special day for him, for NPL, and for Indian science, as his ex-colleagues and collaborators celebrate the Ozone Day in his honor. Former Scientists Forum of CSIR-NPL is a very active forum, which I came to know after joining NPL. And the organization of A P Mitra Memorial Lecture is one heartening example of the healthy research atmosphere they worked in while at NPL, and the respect they accord to each other. For the growth of an organization, as well as to get its due recognition outside, harmony within and encouragement to each other to excel are very important. I admire and thank NPL-FSF for showing the path for the current and future generations of NPL staff. I welcome you all to the 7th A P Mitra Memorial Lecture and look forward to an excellent talk by Professor Patricia Doherty. Thank you.
Thank you very much, Professor Gopal. Thank you again for your full support to our organization. Thank you.
Thank you.
Friends, we are very grateful to the Indian Radio Science Society, InRaSS, who are partnering in the organization of this event by providing support in some key technical and other aspects. The formation of Indian Radio Science Society was actually motivated by the pioneering initiatives taken by Dr. Mitra to promote research in radio science in India and in the developing world. It is my pleasure now to invite Professor S. Ananthakrishnan, the President of the Indian Radio Science Society, to say a few words about Dr. A P Mitra. Professor Ananthakrishnan, please.
Dear friends, on behalf of the Indian Radio Science Society, I feel privileged to talk about Dr. Ashish Prasad Mitra, the doyen of radio science in India, whom I knew very well during his lifetime. He and I belong to the same alma mater, he being much older than me. Dr. Mitra initiated the regional facility for radio science, RFRS, which Amitabh mentioned, and which has morphed into the Society of InRaSS, as Amitabh explained. Dr. Mitra was the director of the National Physical Laboratory from 1982 to 1986, and the Director General of Council of Scientific and Industrial Research, CSIR, from 1986 to 1991, as was mentioned. He was well known all over the world for his work in radio and atmospheric physics. He was born on February 21, 1927, in Calcutta, or Kolkata, as it is called now. A brilliant student all through his educational career, he had stood first in all the major examinations that he attempted. After passing his Master of Science in Physics from Calcutta University, he joined Professor Shishir Kumar Mitra, who was a pioneer of atmospheric research in the world since the 1930s. And the younger Mitra's DPhil degree from Calcutta University on the subject at a time that was considered the golden era of Indian radio physics as well as ionospheric science, marked the first state of a brilliant scientific career. Mitra joined the National Physical Laboratory in 1954 as Secretary Radio Research Committee, and soon afterwards set up the Radio Science Division at NPL, which Dr. Doherty mentioned. And it marked the beginning of an association that was to last for till the very end for at least 50 years. As a successor to his mentor, Professor Shishir Mitra, Dr. Mitra carried the ionospheric research program forward at NPL in collaboration with all the other groups in the country. AP Mitra's research topics involved the Earth's near space environment first, with ground-based and then later space-based techniques. As Secretary of the Indian Committee of International Geophysical Year, IGY, and he steered the Indian program for IGY, as well as the International Quiet Solar Year, which is IQSY, during 1957-58, which pushed Indian efforts into the international limelight and ushered in a new era of ionospheric chemistry. His pioneering research in cosmic radio noise for studying the upper atmosphere led to a series of discoveries in the ionosphere and solar physics. The 60s saw him working in the high-level atmospheric probing with rockets-borne payloads. He saw developing scientific capability in radar and troposcatter system, and under his guidance, the SITE experiment, the Satellite Instructional Television Experiment with radio beacons, led to an India-wide effort on the studies of the upper atmosphere. The Indian Middle Atmospheric Program, which is very well known, IMAP of the 80s, saw extensive use of balloons and rockets to carry equipment up to the ionospheric levels, and the 90s saw his initiative with new world-class efforts. Mesospheric, stratospheric, tropospheric MST radar at Tirupati in South India, and the SROS satellite, which specialized capacities to access substantial parts of the atmospheric environment from near the surface to around 1,000 kilometers for physical properties like electron and ion temperatures, as well as densities at different levels. During the last decade, Dr. Mitra had concentrated on global environmental changes from human activities and their consequent impact on the biosphere. His contribution to the chemistry of atmosphere and measurement of greenhouse gases of India and to global environment chemistry, including the measurements of methane emission from paddy fields, has been significant. As a leading figure in international programs like the Indian Atmospheric Science, Indian Ocean Experiment, INDO-X, he played a very crucial role in the field of global climate change research, and I was quite involved, and I knew what his activities was at that time. Dr. Mitra was the recipient of many coveted honors and awards. He was a fellow not only of the 3 national academies, but also of some of the most prestigious academies of the world, especially the Royal Society, the Russian Academy of Science, and the Third World Academy of Science to us. His awards spanned a very wide range and included the Bhatnagar Award in 1968, Sir C.V. Raman Award in 1980, FICCI Award in 1982, GM Modi Award in 1991, Meghnad Saha Memorial Award in 1992, and the prestigious Padma Bhushan Award of the Government of India in 1987, to name only a few. He was president of the International Union of Radio Science for a term. His professional standing notwithstanding, his human qualities such as love for cricket, Ravindra Sangeet, and his enjoyment in fraternizing with fellow colleagues was no less evident. One of his last scientific acts was an authoritative account of the progress of atmospheric research in India, starting from the pioneering efforts of Professor S.K. Mitra and duly carried forward by NPL under his dynamic leadership as a chapter in a book entitled India in the World of Physics, Then and Now by A. Mitra in 2007. He passed away on September 3, 2007, after a month's illness, to our great shock and concern. Only a few months earlier, his 80th birthday had been celebrated at NPL, the institution with which his name has been inseparably associated for the last half a century. He was survived then by his wife, Sunanda, and two daughters, Anusuya and Putralekha, and their respective families. Mrs. Sunanda Mitra too passed away soon. Our humble homage to both of them. Thank you, gentlemen and ladies, for your kind attention. Thank you.
Thank you very much, Professor Anand Krishnan, for those nice descriptions about Dr. A P Mitra. Now, finally, we are ready for the main event, the 7th A P Mitra Memorial Lecture titled Storms from the Sun, the Science of Space Weather. It will be delivered by an internationally renowned space scientist, Dr. Patricia Doherty. It is my pleasant duty now to introduce the speaker for today. Dr. Patricia Doherty is a leader in the use of Global Navigation Satellite Systems, GNSS, for ionospheric research. She is currently the director and principal scientist of the Institute for Scientific Research, ISR, at Boston College, Massachusetts, United States. As director of the institute, she oversees the activities of staff members working on a variety of innovative research projects. These projects include studies of space physics, space weather, ionospheric and atmospheric effects on space-based systems, ionospheric measurement techniques, chemical reactions in space, and magnetospheric physics. As a scientist, Patricia's own research interests are focused on space weather and ionospheric effects on global navigation satellite systems and its relevant applications. In addition, Patricia has been very active in promoting research and education in the science of navigation in developing countries. She is an associate editor of the Radio Science Journal, a member of the American Geophysical Union, past president of the Institute of Navigation, ION, chair of the International Union of Radio Science, URSI Commission G, the URSI representative to the International Committee on GNSS, the Boston College representative to the university's Space Research Association, and Secretariat for Scientific Committee on Solar Terrestrial Physics, SCOSTEP. Most recently, she was named chair of the Space Weather Advisory Committee for NASA. Patricia is the recipient of numerous awards for research and international outreach, including the ION Burka Award, the ION Weems Award, and the ION Distinguished Service Award, the 2017 GPS World Leadership Award, and the 2018 AGU Carrington Education and Outreach Award. She is a fellow of the Institute of Navigation, URSI, and African Geospace Society. Finally, only 2 weeks ago, Dr. Doherty added one more feather to her cap. She was elected to the very prestigious position of the Vice President of the URSI. Congratulations to you, Patricia. With this brief introduction, I have great pleasure in inviting Dr. Patricia Doherty to deliver the 7th A P Mitra Memorial Lecture. May I request all the rest of you who are logged into the WebEx meeting to kindly switch off your cameras and microphone. Patricia, the floor is all yours. So we are looking forward to your lecture. Thank you.
Dr. Sengupta. I am very, very happy to be here, and I thank you for that very kind introduction. I'm extremely honored to be a speaker in this very important memorial lecture for Dr. A P Mitra, and I hope that he would enjoy this presentation as well on space weather, as he really contributed much to the background information and knowledge in this area. With this, I will share my screen and begin the presentation. And where did it go? Okay, now I'm having trouble sharing my screen.
Yes, we can see your screen now.
Okay. So here is my lecture. Maybe to avoid interference, hold on a minute. Okay, I was going to try to shut off my camera just to avoid distraction, but I can't seem to do that. So anyway, let's talk about the presentation today is storms from the sun, the science of space weather. Quite simply, space weather, the term space weather was coined not long ago in the 1990s, really, to describe the dynamic conditions in the Earth's outer space environment, in the same way that weather and climate refer to conditions in the Earth's lower atmosphere. So space weather includes any and all conditions and events on the sun, in the solar wind, in near Earth space, and in our upper atmosphere that can affect spaceborne and ground-based technological systems, and through these, our human life and our endeavors. So although space weather events have been an occurrence since the beginning of time, it's really only become important to us since the late 20th century. And that's when it became a big problem. And the reason was that society became dependent on space-based infrastructure. And with this increasing independence on space-based infrastructure in our society, space weather has become more and more important for us all to have a general understanding and to define, to model, to predict, and to mitigate for some very large possible events. And this is what we'll talk about in this presentation. So the outline is quite simple. We'll introduce the physical concepts of space weather, which include, of course, the sun, since that is the source of space weather. We'll talk about solar eruptive events, the solar wind, and then that very important sun-Earth connection. Then we'll look at some of the impacts, radiation, power grids, satellite drag, satellite damage, the ionosphere. Certainly there's a strong connection between space weather and the ionosphere. And then, of course, GNSS and the many applications related to it. We'll finalize talking about some of the international collaborations that are ongoing to forecast and mitigate space weather. So let's start with the sun. So the sun certainly is the source of all space weather. And the sun lies at the heart of our solar system, where it is by far the largest object. It is composed of the sun and all things that orbit it. There are 8 planets, asteroids, and comets. It's really quite old, 4.6 billion years old, in fact. It's 99 million miles away from Earth. It does hold 99.8% of the solar system mass, has a diameter of 864,000 miles, which is 109 times the size of the Earth's diameter. In light years, it is about 8 minutes from Earth. It's really just a hot ball of plasma, comprised mostly of hydrogen and a little helium. It's very powerful, and we know that it would take 100 billion tons of dynamite every second to match the energy provided by the sun. So although it's powerful and central to our life on Earth, it is a rather ordinary star in the universe. In fact, there's just one of more than 200 billion stars in the microwave, shown out here, in the Milky Way galaxy. This is some 25,000 light years from the galactic core. More information about the sun. The sun, as shown on this illustration on the left, is divided into 6 layers from the center out. The layers of the sun are the radiative zone, and then the convective zone. Then there is the visible surface known as the photosphere, the chromosphere, and finally the outermost layer, the corona. The energy produced through fusion in the sun's core, it powers the sun and it produces all of the heat and the light that we receive here on Earth. But it's not just a big bright ball. That process by which energy escapes from the sun, it's quite complex, and it's complicated with those complicated magnetic fields that form sunspots in active regions. The sun also sends out a constant flow of particles with the solar wind, and it occasionally erupts with giant clouds of solar material called coronal mass ejections, or explosions of X-rays in the form of solar flares. So these events can certainly rattle our space environment out to the very edges of the solar system. And this really is the onset of space weather. So major space weather events, CMEs, and flares, however, do not happen every day. In fact, significant events are tied closely with the solar cycle. The figure that we're showing you here is the yearly mean sunspot count since 1700. Sunspots have been counted since the invention of the telescope, however, since the early 1600s. So the approximate 11-year solar cycle that you're looking at here is really based on the number of sunspots observed on the sun, with high numbers referring to solar maximum and low numbers referring to solar minimum. The 11-year cycle is tied to the time it takes for the sun's magnetic field to flip. This means that the sun's north and south poles switch places. Then it takes another 11 years for the sun's north and south poles to flip back again. Sunspots are caused by the sun's magnetic fields. As the magnetic fields change, so does the amount of activity on the sun's surface. Near the minimum of the solar cycle, it's rare to see sunspots on the sun. And the sunspots that do appear are very small and they are short-lived. During solar minimum, however, space weather effects can be found, but they will be minimized. But they are not impossible. It's important to note that the most recent solar cycle, 24, where I'm pointing this green arrow, was the lowest solar cycle in the last 100 years, comparable to that solar cycle 14 shown over here on the bottom side that occurred in the early 1900s. Here's another image of sunspots. This is an image of the daily sunspot numbers from 2009 to the present. This goes up to September 1st. And you can see here that the solar cycle began around, the current solar cycle 25 did start. It started in December 2019. Activity is still quite minimal, with the current sunspot number near about 30, I think. You can also see that solar cycle 25, shown out here, is starting to develop much like the last one, solar cycle 24. But there are no guarantees yet. We could certainly have a bigger cycle, but it looks a lot like the beginning of solar cycle 24. So this figure illustrates that there's a lot of day-to-day variability in the number of sunspots. It's certainly not a smooth number like we saw, on the last plot. The figure illustrates that there's that great variability. Yellow is the daily sunspot number. Blue is the monthly average number. Red is the monthly smooth sunspot number. And those red dashed lines shown far to the right are the predictions for solar cycle 25, using two different techniques for sunspot prediction. So you can see that the predictions are quite different. And this figure I have downloaded from the Royal Observatory of Belgium. In fact, if you want to keep up with the sunspot, they have a very good, almost a daily update on what's going on. So I think it's no question then that space weather does begin at the sun. In fact, it begins with that sunspot that we just talked about. Sunspots are visible on the sun, and they are darker than the surrounding surfaces. They're darker because they're cooler, and they're cooler because of the intense magnetic fields within them. These magnetic fields are in fact so strong that they keep some of the heat from the sun from reaching the surface. The figures on the left show just how visible these sunspots are. The bottom figure shows just how big they can be by comparing it to the size of Earth. Solar active regions, depicted in the middle plot there, are regions where pairs or clusters of sunspots are associated with the release of energy from the photosphere. That exact mechanism that causes the explosive release is really unknown, but we do know that they are related to the rapid conversion of magnetic energy into particle kinetic energy near those very strong magnetic fields. The twisting of the surface of these magnetic fields leads to that release of energy, and these active regions are the source of solar flares and CMEs. So solar flares, they're really the largest explosive events of our solar system. There's a couple of movies here illustrating a couple of solar flares. They are characterized by intense releases of energy in the form of radiation and electrically charged particles. Radiation can travel at the speed of light, while the charged particles certainly move much more slowly. There are three classes of flares based on X-ray energy, C, M, and X class flares. The X-class flares are certainly the strongest solar flares that the sun can unleash. When aimed directly at Earth, they can disrupt communication and GPS navigation systems on Earth, and even pose a threat to satellites and astronauts in space. M-class flares are about 1/10 of the size of X-class flares, but can supercharge the Earth's auroras still, or the northern lights, resulting in those dazzling aurora displays. Can also cause some disruption to our near-Earth space environment. Solar flare impacts include many. So there are here are some actual system impacts from a few of the most intense solar flares that occurred in 2003. This was a very high solar cycle, 2003, as compared to the most recent solar cycle, 24. This flare actually saturated X-ray detectors on several monitoring satellites, resulting in the loss of Japan's Midori satellite. We saw anomalies on about 30 other satellites. Effects were actually felt on 2/3 of all of the NASA satellites. It was the first time that the FAA issued a first ever passenger alert. The FAA WAS system, which we'll talk about later on, which is a civil aviation navigation system, started to show errors exceeding 100 meters. Satellite communications were interrupted, and the electric power service failed in Sweden. This was probably the largest solar flare ever recorded, and it was recorded in November 2003, really at the peak of solar cycle 23. So CMEs, the CMEs are actually intense solar events. They are characterized by huge bubbles of plasma ejected from the sun that speed into space. They do disrupt the flow of the solar wind, and they produce disturbances that can strike Earth with sometimes catastrophic results. These do occur over very large sunspot groups, and they're very often associated with large solar flares, as this one was. CMEs are really the most threatening of solar events on technological systems, as they can induce geomagnetic storms on Earth. And if you want to compare this to what happens in our terrestrial weather, it's the equivalent of a hurricane. In fact, they typically reach Earth. They can reach Earth in sometime between 1 to 3 days after the eruption of the sun. And once again, it is the most threatening of solar events on technological systems. The picture on the right was captured on January 8th, 2002. It shows an enormous eruption of a CME spreading out to space. It's a composite of two SOHO images from two different instruments. The background's an image taken from the SOHO coronagraph. It's an instrument that blocks the bright face of the sun, allowing us to see the fainter solar atmosphere. The coronagraph image also shows a widely spread CME as it blasts more than 1 billion tons of material out into space at millions of miles per hour. The sun seen at the center of the image is just made for a very nice image. It was actually captured by the SOHO's EUV telescope on a different day. So the solar wind, let's talk about solar wind. Solar wind is also a very important phenomenon as it carries solar mass, atmospheric mass, momentum, and energy due to solar flares and CMEs into space. The solar wind streams in all directions, and they are changing in speed. It actually moves faster over the coronal holes, showing you there with that top red arrow, at speeds of about 800 kilometers a second, and slower over the lower latitudes on the sun at speeds of about 400 kilometers per second. The source is really the sun's, the source of solar wind is really from the sun's corona. And from what I understand, the sun's corona is so hot, the magnetic fields cannot hold on to all of this plasma, and thus the solar wind takes it and buffets the Earth's magnetic field. And as I said, this can certainly produce magnetic storms. The image that we're looking at is data taken from NASA's and ESA's Ulysses spacecraft. This is data for 1.3 to 5.3 astronomical units. This system measures the variability of the solar wind. Unfortunately, it was retired in 2009. However, the ACE satellite continues to monitor solar wind along with some other newer satellites. So here is a classic case of a magnetic storm. It shows a NASA animation in the center. It shows as I mentioned, large solar flares and CMEs induce solar and magnetic storms on Earth. They're typically in response to large flares that burst from the sun with great speeds. You can see it carrying billions of tons of plasma into the solar wind. And the Earth's magnetic field normally deflects much of this solar wind, but under intense conditions such as this one, we can see that particles then enter the Earth's magnetic field where the lines connect on the anti-sunward side of the Earth, and it results in aurora and a geomagnetic storm. So the effects of the storms include degradation of satellite instruments, introduces dangerous particles to electronics and people. It can disrupt GNSS and satellite communication, and it has potential to introduce drag on satellites, changing their orbit paths. And finally, we can see many GNSS position errors due to a magnetic storm such as this. So the animation I just showed in the last slide really depicts a very strong magnetic storm, but the interaction between the sun, its plasma wind, and the Earth's magnetosphere is what we call the sun-Earth connection. It's really important to note that the solar wind is constantly flowing, but under normal conditions, the Earth's magnetosphere deflects it. Under intense conditions, as we just saw in the NASA animation, the particles can enter the Earth's magnetic field where the lines connect on the anti-sunward side of the Earth. In fact, you know, that solar wind doesn't just come back towards the Earth. It doesn't face just in our direction. That would be somewhat centric for us. It goes in all directions. In fact, it can reach as far out as Pluto and Neptune. Coronal holes can also be a source of geomagnetic storms. They appear as dark areas on the solar corona in extreme ultraviolet and soft X-ray images. Coronal holes are cooler, less dense regions than the surrounding plasma. And there are regions, the regions are open, they're unipolar magnetic fields. The open structure allows charged particles to escape, resulting in streams of relatively fast solar wind. This solar phenomena can also result in geomagnetic storms. In fact, coronal holes are the prime source of storms in solar minimum. However, they're not generally as severe as those caused by CMEs. So one of the more benign consequences of space weather, and one of the prettier ones, is the aurora, which we know better as the northern and southern lights. A bright aurora signifies a strong disturbance in the upper atmosphere in the magnetic field of the Earth. This happens when excited particles from the magnetosphere collide with particles on the Earth's upper atmosphere and electrically excite them to emit light. So the aurora usually appears between 60 and 80 degrees in latitude, and it expands equatorward under very intense conditions. The aurora is really the only visible sign that the Earth's magnetosphere has been disturbed. However, much of what we call space weather is invisible to the naked eye and can have much more serious consequences. One of those is radiation. In fact, a major source of radiation exposure from air travel, radiation can certainly be a problem for air travel. In fact, the major source of radiation from air travel comes from the flight itself in the form of galactic cosmic rays. The figure on the top right shows the smooth monthly sunspot averages from 1960 to 2009. This is shown on top, and these were based on counts of galactic cosmic rays that were recorded in Antarctica by the University of Delaware. And here we see that the galactic cosmic rays are actually anti-correlated with solar activity, so they really are not a space weather phenomenon. However, when these galactic rays are combined with episodic eruptions from the sun, they do produce and scatter additional high-energy particles into a broad ionizing shower, producing additional harmful radiation and health effects. The figure I'm showing now on the top right, it shows the amount of radiation you can be exposed to during a normal commercial flight. Typical commercial aircraft do fly at about 30,000 feet, and they're exposed to approximately 3 microsieverts per hour. This is a measure of radiation exposure. However, as you go higher in altitude, the exposure increases. And the reason is because at high altitude, the air gets thinner. And thinner air, of course, means that there are fewer molecules to deflect those incoming galactic cosmic rays, that radiation from outer space. This means that high-flying jets, the International Space Station, and future space travelers can be exposed to harmful galactic rays. This is particularly risky for high-altitude flights, astronauts in travel, and the ISS, although the ISS is shielded to protect its residents from storms. Oh, what we need to be concerned about are future space flights that are now planned to the moon and Mars, as they're going to require something even more protective than what is probably in the ISS. So radiation from space weather events is also risky to commercial flights over the poles, where there's less protection from the Earth's magnetic field during solar storms. Airlines reroute these high altitude flights to avoid an increase in radiation, but it's a very costly process. I think this is a couple of years ago, the cost of redirecting one of these flights exceeded over $100,000 per flight. Another space weather effect is on satellites. Space weather also has effects on our satellites. Some of the problems include energetic ions that can damage solar panels, energetic plasmas that can cause electrical charges that can damage the electronics. It, as I mentioned before, can increase satellite drag. There's an economic value of our satellite enterprise. Satellites cost a lot of money. They're out there to help protect us and for our own space research, but the economic value of our satellite enterprise exceeds over $100 billion. We need to protect this enterprise. Some of the results of storms on our satellites, we saw that in March 1989, a very large storm, we saw more than 1,500 satellites slowed down during that storm. We saw that 2 satellites shut down in 1994 during magnetic storms. We saw at that time telephone services in Canada were disrupted for months. In 1996, we saw 14 satellites disrupted due to storms, with $2 billion in losses. And during the storms of October 2003 2 satellites were severely damaged. So we also see space weather effects on our electric grids. These storms can be quite damaging. So geomagnetic storms do induce currents in our ionosphere that results in magnetic field variations. The variations can cause currents to flow along any conducting path on Earth. These electrical currents are known as geomagnetically induced currents, or GIC. They can surge along oil and gas pipelines and also high-tension electricity lines via ground transformers. The extra current in these power lines can burn out transformers, leading to large-scale brownouts or blackouts, while the electricity in our pipelines can enhance the rate of corrosion. It's estimated that transformer failures across the US and Canada caused $100 million in equipment damage each sunspot cycle. Here we're showing the results of a transformer failure at Hydro-Quebec, Canada, with 6 million people lost power for over 9 hours. And this was in response to a large geomagnetic storm that occurred in March 1989. So space weather also has effects on radio signals and HF communication, primarily because all those signals meet the ionosphere in some way. So the ionosphere, just shown on the left, is that part of the Earth's upper atmosphere. Extends from about 80 kilometers to over 1,000 kilometers. It's the area where the number of charged electrons or electrically charged particles is large enough to affect the propagation of radio waves that are used for both communication and navigation. So the figure that I'm showing in the middle there is an old one, but I think it explains this phenomena quite well. We can see that on frequency, that is low frequencies, that is frequencies below 30 megahertz, the ionosphere actually reflects the signals, allowing for long distance communication. At higher frequencies, however, radio waves will pass right through the ionosphere, but not without the ionosphere first modifying those signals. Solar disturbances can make the ionosphere even more chaotic than usual. And during those times, HF communication can be degraded and interrupted. This is for ham radios and AM radios. GPS signals can also be degraded, interrupted, and scintillated during these events. So before we talk about space weather effects on navigation, I'd like to just point out some key points about GNSS systems. GNSS refers to a constellation of satellites that provide signals from space to transmit positioning and timing to GNSS receivers on the ground or in space. There's currently 4 global GNSS systems, operational and nearly so. And there are also 2 regional systems, and you can see certainly the InRaSS of India is one of those regional systems. All of these systems are designed to provide position, timing information 24 hours a day, 7 days a week, under any weather condition, anywhere in the world. There are 3 segments there's certainly 3 segments: the space control and the user segment, and you can see those here on the right. For the user segment, we certainly have, we're all users, whether you are aware of it or not. You and about 200 or 300 million other people are certainly using GNSS in some way. So what's important to know is that GNSS signals are very weak. So there's also long distance between the satellite and the receiver, and GPS signals result in high attenuation of the signal. The signals will be affected by space weather, primarily because they propagate through the ionosphere, where we feel the effects of space weather. In fact, the ionosphere is the most significant source of error for GNSS. Certainly other vulnerabilities and challenges for GNSS, unintentional interference, jamming, and spoofing, but those are not a concern for our presentation today. So the ionospheric effects, the ionosphere does have major effects on GNSS navigation, even on a calm day. So it affects it in the fact of, with range errors, it induces ranging and time errors under normal conditions. These range errors are due to the change of the speed of the signal, and they're presented as both the group delay of the signal modulation, which results in an absolute range error, and also a carrier phase advance, which gives you a relative range error. These range errors are proportional to the total electron content with a very simple formula. And the values of range error really do vary from about 1 to 100 meters. Another issue another ionospheric issue is really scintillation. Scintillation is due to the rapid fluctuations in the amplitude and phase of the signal. The feature can induce losses of lock on the signal. Scintillation is certainly rare in the mid-latitudes, but it can be very serious after local sunset in the equatorial region, especially near the peak of the solar cycle. There are other effects that the ionosphere has on GNSS and all radio signals. They are listed there, but we won't be discussing those here today either. The figure on the right shows an example of a GPS signal passing through a nominal quiet ionosphere here, yet it still results in a ranging error. It also shows the effects of scintillation when a GPS signal passes through a patch of ionospheric irregularities, scattering the signal and resulting in losses of lock on the signal. This figure here was taken to a very good, if you're looking for a beginner's guide to space weather and GPS, a very good guide that was originally written by Professor Paul Kittner. Good thing to remember is the ionosphere is quite variable. What I'm showing you here is a typical map showing worldwide TEC that's been produced with IGS data. This is from March 17th, 2015. So as mentioned in the previous slide, TEC is the integrated electron density along a path between a receiving station and the satellite. What the figure illustrates is the geographic variations in the ionosphere. Although this figure is static in time, I'm thinking that it's likely around midday in the Indian sector when the ionosphere is at its highest level of ionization. And you can see that it's depicted here in red. However, as the day goes on, we'll see those local time changes, and these high levels of TEC will then move from east to west. That area where we also see those highest values of TEC lies in the regions north and south of the magnetic equator. And these are known as the equatorial anomaly regions. It certainly is where the highest density of TEC is recorded, but it's also where ionospheric irregularities occur in the form of scintillation in equatorial plasma bubbles. Scintillation, as I mentioned, is a rare occurrence in mid-latitudes, but we only see phase scintillation in response to geomagnetic storms. At high latitudes, it's much more common, and it's increased during geomagnetic activity. But at low latitudes, scintillation is common, and it's not really induced by space weather. Rather, it's by an equatorial electric jet force that introduces a higher density of plasma in irregularities in the equatorial region. And we'll talk a little bit more about that in just a moment. So this is an example of large gradients that can be introduced into the ionosphere and in GPS measurements during a significant space weather event. On the left are the ionospheric measurements during taken from a number of GPS ground-based receivers on a quiet day. These receivers were part of the wide area augmentation system developed by the FAA that enables civil aviation. The circles on the plot refer to the ionospheric pierce point location, and the plot cover and the sticks emanating from the circles are actually pointing to the GPS receiver that took that measurement. So this plot covers much of the contiguous United States. The left plot shows a very quiet ionosphere with between 0 and 5 meters of range error over the entire region at this time. The plot on the right, however, shows a much different picture with a very strong gradient reaching diagonally over the whole coverage area. This feature is actually known as a storm intense density, or an SED, and it has been studied widely in the literature. In a WAS system, this type of behavior would lead to a loss of availability to use the system in the region due to those strong gradients. And it's primarily due to the decreased accuracy and integrity of the system during that time. So the event we're talking about here is the Halloween storm of 2003. This is a period of great geomagnetic storm activity with several storms that occurred between the period of October 29th and 31. The figure on the left here is now showing the decrease in accuracy seen from the network of receivers during that time. In black, we can see the horizontal errors that were seen for a WAS receiver, and in color are the errors recorded from 4 differential GPS systems from the Canadian differential GPS network. And what you can see is we see very, very strong horizontal errors during the times when we saw those geomagnetic storms. Also, here's just an example of ionospheric scintillation, an effect on GPS signals. As mentioned, scintillation both amplifies and fades the GPS signal. On the left, we're looking at measurements taken at Ascension Island. This is an island off the coast of Africa where we very often see some of the most intense scintillation. This was data taken in March of 2002 at the peak of a high solar cycle. On the left are signal-to-noise measurements from the L1 GPS signal on the top, and from the L2 GPS signal on the bottom. This is now just from one GPS satellite using a rather older receiver during 2002, but this was taken during a time of intense scintillation. The red pieces shown here on the left are where the signal faded enough that it was no longer able to use GPS to calculate a position, meaning we were tracking less than 4 satellites. On the right, we see the results of scintillation fading on the position calculated with GPS. In this plot, the Ascension Island is at the center of this plot, and the data, the dots reveal this calculated position from GPS. They are quoted according to the scintillation, with red being S4 of 1, which is about as high as it goes, basically. That's very high scintillation. So the resulting position areas, you can see this is north, south, east, and west. They really got as high as 75 meters out here in the horizontal plane, and they got as high as 50 meters in the vertical plane. So ionospheric scintillation fading can seriously affect GPS positioning. So this is an example of low latitude scintillation at solar maximum. However, effects will vary based on solar activity. As I mentioned earlier, scintillation is more prominent in the low latitude regions and high latitude regions, and often during solar storms, scintillation is often suppressed in those low latitude regions. And this is one of the reasons we refer to scintillation really as a quiet time space weather effect. In fact, 1/3 of the Earth's surface is affected by equatorial features. Here is where equatorial scintillation generally occurs between 2000 hours and 01 local time in the seasons that are shown in the plot. And as you can see here in India, it is most active in the equinox periods. The most severe effects are also observed in higher levels of solar activity than in lower. And finally, the equatorial anomaly depicted in this figure include the highest levels of where we see TEC, the strongest gradients over latitude, and also all along here in these anomaly regions, the most significant levels of scintillation and bubble occurrence. So as I mentioned before, the phenomena that's responsible for scintillation in the low latitudes is really much different than space weather events. Rather, it's formed in response to an electrodynamic force. It's where vertical drift velocities lift that F region plasma to higher altitudes over the magnetic equator. From these pressure gradients, we see pressure gradients and gravity force that heightened plasma downwards along the magnetic field lines. So it lifts up over the magnetic equator, and then it's forced along these magnetic field lines. So it's important to know that the strength of those drift velocities is highly variable. So the higher, the stronger that drift velocity, the higher over the magnetic equator it will go, and that means that it will go out further to areas farther north and south of the geomagnetic equator. So also, and we see that we see this happen during the day for sure, but there's also a strong post-sunset E cross B phenomena that can cause an instability process that then propagates a hole in the plasma to anomaly regions where we see depletions and scintillation. So India, as you saw in the last plot, spans the entire low latitude region. What we're going to see in the next few slides are some measurements of scintillation that were recorded as part of the CINDA program, and much of this information is courtesy of Keith Groves, one of my colleagues at Boston College. So going to look at data both from Tirunelveli, which is situated close to the magnetic equator, and Kolkata, which is firmly in the anomaly region here. So what we know is that the occurrence frequency of spread F is higher closer to the magnetic equator. However, it is more intense and severe in the Appleton or the equatorial anomaly regions. This is historical information. So what we'll see is simultaneous GNSS observations from both of these stations will demonstrate important aspects of the structure and dynamics of the equatorial ionosphere. So here first we'll look at the GPS scintillations. This is from solar cycle 24, so this is the lowest solar cycle, and this is from our equatorial station, Tirunelveli. These are GPS L1 scintillations from this station from the years 2010 to 2015. We are just looking at the highest elevation satellite, looking at what the L1 amplitude scintillation would be from that location. And what we see is that activity and severity increased beginning in 2010 as solar flux began to increase to the maximum in 2014. So it was 2010, 11, 12, 13. You can see it get a little bit worse each year until 2014. And we see that the strongest activity peaks are, it's a moderate scintillation because it is S4 of 0.5. So it's actually moderate scintillation. Now we look at our anomaly station. This is, once again, same time period, measurements taken from Kolkata. This is GPS L1 scintillations from 2010 to 2015. And what we see here, and this is the anomaly station now, very little activity in 2010, 11, 12, 13. We really don't see anything until March, April 2014. And when it does occur, it's still moderate scintillation of 0.5, maybe a little bit greater than 0.5 in this particular location. How do we explain this result? Well, bubbles originate around the magnetic equator. We showed that in one of our last slides. So all activity is observed from a site like Tirunelveli, which is close to the magnetic equator. However, the density is quite low over the magnetic equator, so S4 will be moderate, and that's exactly what we saw. But when I explained that, you need those bubbles, that you need that activity, the plasma bubbles, to reach well over the magnetic equator to reach out to those anomaly regions. This is what happened. So we know that bubbles need to reach at least 1,000 kilometers altitude over the equator to map northward towards Kolkata. And this happens really only when the solar flux is high. But when bubbles do reach anomaly latitudes, the perturbation occurs and high electron densities do result in much stronger scintillations. And we did see that we got somewhat larger scintillations at Kolkata. However, we didn't see it until March or April 2004. And that is when certainly we saw solar flux units get a little bit higher, but for just a very short period of time. So we do see that bubbles occurred frequently at Tirunelveli, but during the entire solar cycle of 24, they only reached Kolkata consistently during this period. And that's when the solar flux peak over 160 solar flux units. So what are those implications for solar cycle 25? Well, we do know that solar cycle 24 was the weakest solar cycle during our space age, and that's depicted here in this plot. We don't know what solar cycle 25 will hold, but we do know that solar cycles 23 and the two before that exhibited solar flux values well above the peak of what we saw in 2014. So such conditions, such as those prior 3 solar cycles, would undoubtedly cause frequent severe spread out over both central and northern India. And this has been reported by many, many studies in the past. The impacts of such activity may be critical now, given the ever increasing reliance on space-based services, such as navigation and the Indian NAVIC system. It's important to recognize that stronger space weather events are likely in the near future as we rise into solar cycle 25, and thus the need for us to continue to maintain robust monitoring and preparedness programs has never been greater. This is another effect. We'll talk a little bit more about solar cycle and what we can expect in later slides, but this is just another effect on GNSS, and these are solar radio bursts. So we do see, the solar radio bursts are intense radio emissions from the sun. They are associated with solar flares. We see strong solar radio bursts can impact can certainly impact GPS receivers, and I give you a couple of references there. On December 6, 2006, there was an X6 flare, which was really the largest solar radio burst in history, from 500,000 to 1 million solar flux units at GPS frequencies. We saw significant effects on GPS receivers over the sunlit hemisphere. Here we show some of the results of that. These were, once again, the solar radio burst. It had some intense radio emission from the sun. It was associated with solar flares. And we saw significant effects on GPS receivers over all the sunlit hemisphere during that time. Here we show on the top, we're looking at that those green dots are GPS receivers tracking 4 or more satellites. And this is at a certain time, 12:29 UTC. Just a few minutes later, 3 minutes later, we're now seeing red dots showing that GPS receivers were tracking fewer than 4 satellites, and thus it was unable to calculate a position. So the largest solar flux unit was seen at 1.6 gigahertz between 1930 and 1936. And what happened is we lost tracking for nearly 5 minutes on the full sunlit hemisphere of the Earth due to this solar radio burst. So, as we mentioned earlier, one of the most dominant error sources for GNSS applications is the ionosphere. And this becomes even more apparent during extreme solar storms. when strong gradients, solar gradients due to cause storms, and scintillation can further compromise the performance of many applications. Some GNSS applications specifically affected by space weather include many of the things listed here. And many of these, of course, are involved in every facet of our daily lives. We go from wireless technology, cell phones. I'm sure we all have at least one or two cell phones. Mine is sitting about 6 inches from me. It affects pipelines, geographic exploration, surveying, continental and fiber optic cables, surveillance. Our banking systems are based on the timing systems of global navigation systems. Of course, there's so much remote sensing, emergency location systems, natural resource monitoring, all modes of transportation, both on land, sea, and air. Agriculture, of course, is affected by space weather as well. In the system I've had an opportunity to observe more closely are aviation systems. In fact, aviation augmentation systems such as SBAS and GBAS systems. The atmosphere and space weather are challenged certainly for those systems. The map on the bottom here is actually a YouTube map showing the increased demand for aviation and aviation services. So SBAS and GBAS systems, I'd like to show you a little bit about that. They're augmentation systems for civil aviation. SBAS systems cover a wide area or a regional scale, such as the FAA's WAS system, which covers much of the US and parts of Canada. And this is a system I have had the great opportunity to work on. India also supports an SBAS system called Gagan, which was developed by Israel. GBAS systems are local area systems, and they may cover an area that is much smaller in magnitude, usually around a particular airport. The thing to note is that these systems hold important roles in aviation safety. They ensure accuracy, availability, and integrity of navigation information. They primarily operate by broadcasting routine correction messages, allowing for navigation control systems to correct for the ionosphere and to provide precise positioning calculations. Important to note that those large space weather events, such as CMEs, can induce large errors in the system, limiting availability of the system. Here are some examples of space weather effects on WAS during solar cycle 24. The figure that is on the top left represents a nominal or undisturbed condition, where we see 99% availability of 100% of the CONUS, 81% of our Alaska, and 95% over Canada. This is really the best possible scenario for us, and we see it most days. The plots that follow, however, show various degradations in availability during storm days. The top middle, we can see here that 99% availability, which is what we are looking for, is degraded, and now we just see it available for 91% of the CONUS. We've lost availability in Alaska, and we had no information from Canada. And this was due to a storm with a KP value of 7, which is a geomagnetic storm index. That storm happened in October 2012. There was another one in November 2012, where again we saw some losses of availability in Alaska and Canada. In 2013, more losses, once again, mostly affecting Alaska and Canada. Much of the contiguous US remained stable. Over here, this is one of the biggest effects we saw. This was actually a KP of 6 storm, happened in February 2014, and that we lost availability down to 39% of Canada, and we lost all of availability in Alaska and Canada. You can pick up on this website here in the FAA that does show day-to-day variations, day-to-day availability of the WAS system. So as we're talking about the solar signal, as you have seen, many GPS satellites are affected by space weather. However, significant problems in space weather events are closely tied to the solar cycle. The figure on the left shows the solar cycle since 1750. However, Galileo saw them first in the early 1600s, and they've been counted ever since. We're currently here at the beginning of solar cycle 25, where there's been a small uptick already here, a small uptick already in the number of sunspots, together with some smaller solar events that have already caused aurora and minor effects. Predictions have shown that solar cycle 25 will likely be similar to the size of solar cycle 24, but no guarantees yet. We certainly have plenty of time for that cycle to rise above what we're anticipating. One thing to mention is that this last solar cycle 24 was as low as the solar cycle that was experienced nearly 100 years ago in solar cycle 2014. The things we need to be concerned about, however, are the largest storms, some of which we have referenced in this presentation. The figure on the left I've edited to show when these large events have occurred. And they usually happen near the peak of solar activity, near the peak of the solar cycle, or really just past the peak. You can see here they occur just past the peak. Those big storms, Halloween storms of solar cycle 23, really occurred just past the peak. Some of these events are listed here, also listing here under the most historical solar storms. The largest storm in history, and one that none of us have experienced, was the Carrington event that occurred in 1859. This is one that hit Earth directly, and it actually caused telegraph lines to spark, setting fire to telegraph offices. However, at that time, we certainly were not dependent on space-based infrastructure. It's important to know that solar storms can happen at any time, even at solar minimum. In fact, there was an extreme CME that occurred July 23rd, 2012. This is a huge CME that tore through space at about 3,000 kilometers a second. In fact, it was 4 times faster than a typical CME, and it was the fastest CME ever seen by NASA's stereo satellite observations. Luckily, it narrowly missed Earth. However, if it had happened 1 week earlier, it would have been a direct hit. The computer model on the bottom left shows that the location of the Earth, I can point it out, location of the Earth is here, with the sun in the center and the CME plasma cloud hitting the stereo B satellite shown here. And that turned out to be a good thing, because the measurements have verified that it actually missed us, because the measurements have verified that this was a CME that could have rivaled that Carrington event in 1859. So a study by the National Academy of Science has found that a Carrington event today could cause huge damage. It could cause $2 trillion of damage in the North American continent alone, and it would take years to make the repairs. The reason is that much of our infrastructure and our technology is now dependent on satellite and space technology. That's GPS, GNSS, communication systems, aviation systems, the internet. We would all suffer serious damage if we had something like a Carrington event. But we point this out just to tell you that even during quiet times, and 2012 was a quiet time, big storms can happen. Thus, we do need to be prepared. So, space weather is important, and research indicates that severe space weather has the potential to disrupt our critical infrastructure with significant consequences to our citizens. As such, governments around the world have responded, and they're working on or have produced space weather strategy and action plans. The U.S. released their first strategy and action plan in 2014, and this was updated in 2019 with a cohesive all-of-government plan delivered to mitigate, respond to, and recover from a major space weather storm. Most recently, the ProSwift Act became public law in October 2020. The purpose of this is to mandate work to improve the ability of the U.S. to forecast space weather events and mitigate its efforts, and to work internationally to do all of this. As mentioned, other nations are doing the same, and we are working together as space weather is a global concern. So an example of an international space weather service is the ISIS. This includes 21 regional warning centers around the globe. And their mission is to improve, coordinate, and deliver operational space weather services. You can see here the picture on the bottom left is showing the SWIPC service in the US, but I'm also showing that India participates with an ISIS center at the National Physical Laboratory, and they joined quite early on, and I'm sure that Dr. Mitra had something to do with that. So ISIS is organized and operated for the benefits of the international space weather user community. However, on the right, as we flip through the next pictures, we can see that we are all working together for certainly to come together, working together with this global concern. So in addition to all of those awareness plans and plans to work together, it's also good to note that NASA operates a system observatory of heliophysics missions that utilize the entire fleet of solar, heliophysics, and geospace spacecraft to discover the processes at work throughout the space environment. In addition to its science program, the NASA Heliophysics Division routinely partners with other agencies to fulfill the space weather research and operational objectives of the nation. Some of the examples of the systems include the ACE measurements of interplanetary conditions from the Lagrangian point L1, where objects are never shadowed by the Earth or the Moon. We also see CME alerts from SOHO, stereo beacon images of the far side of the sun, And we also get super high resolution images from the STO. Launched in 2018, the Parker Solar Probe is a robotic satellite to probe the solar corona and to observe the start of solar wind. In addition, in the future, they are planning the atmospheric wave experiment, which will be fixed on the exterior of the International Space Station. I think that's planned for launch in 2022. And it's also important to note that the US, Europe, and UK have joined in a mission to monitor space weather on the sun and in the solar wind by placing a spacecraft at the L1 and L5 Lagrange points. So to facilitate and enable this cooperation, NASA does make its research data sets, models continuously available to all of us, to industry, academia, and other civil and military systems and interests. So in summary, this has been a long presentation, but I do love talking about space weather and all that and where it comes from and what it does to us. But in summary, we've learned about the sun. We discussed our most disruptive solar events and eruptions. We observed space weather effects on society. We looked at GNSS response to space weather. We are all dependent on many of those GNSS systems around the world. You can see in the mid-latitudes, we see large gradients. In the low latitudes, you see still large gradients, but also scintillation and bubbles. And we also see effects from solar radio bursts. We saw that GNSS applications, many of them, are also affected by space weather. We talked about that near Carrington event of 1859 that missed Earth in July 2012. And of course, that was a good thing it missed Earth. But I think it's more important than ever that we continue to study and know how to predict and plan and mitigate events such as that could happen in the future. So right now, solar activity is low, but solar space weather can happen at any time. And we are starting to see some space weather events causing issues for all of us. And finally, it's important to note, and we are all working together in international government levels, these efforts are in place for the fortification and mitigation of space weather. And with that, I do thank you for your attention. I am delighted to be here with you online. That's just a picture of my favorite spot on Boston College. It's the Baptist Library. I hope that you will come and visit us someday, and I'll give you a tour of that wonderful library. That's my my information, how you can get in touch with me at any time if you'd like to talk about one of my favorite topics, space weather. Thank you.
Thank you very much, Patricia, for that wonderful lecture. You have indeed touched upon a very relevant and very important topic, that is the space weather, which is an emerging field of space science. And we realize now how the sun influences the Earth's space environment, and it impacts all of us. I mean, we as a society are ever increasingly dependent on the space-based technology, and that's where the solar storms hurt us the most. So you've indeed described very elaborately all the aspects of space weather, and also touched upon the international plan of forecasting and mitigation of the space weather phenomenon. In particular, you know, what I feel very scared after listening to your lecture is every time now I travel, you know, between here and the United States on a very high flying airplane, and should there be a solar storm, then I get a lot of radiation on me. It's very scary. So I'm sure you'd like to answer some of the questions which our you know, attendees have. Would you like to answer some questions?
Yes, if I can, sure.
Sure. So may I request all the participants in our panel, if somebody has a question or a comment, please switch on your camera and turn on your microphone, and then you could ask a question. Yeah, Prasannan Krishnan, please go ahead.
Yeah, Patricia, there was a recent news that the scientists have predicted a chance of about 1% or 1.6% to maybe 10% or 15% of a very severe solar storm taking place. I do not know at what time. How have these people made such a prediction? Are you aware about this?
Certainly, they're monitoring the sun very closely. They see a very, very large CME. They monitor it. They start seeing where the CME and the solar wind will travel. I haven't heard a prediction of, we will get certainly a strong storm like the Carrington. It certainly happened before in the past, 1859. So we know that history can repeat itself.
Yeah.
And we did see something like it in 2012. Certainly, I think I'd rather see we, postpone that a few years until we really know how to plan and mitigate for those things.
That's right.
So certainly there are plans in place, particularly like with the power grids. If we see one of those things coming in our direction, I think the plan is to brown out certain power grids so that certainly, if we lose one, we have others so that we don't have those massive losses of power. With radiation, I mean, we already know, we see anything that's coming in our direction, already those high altitude, high latitude flights are being rerouted down in altitude and certainly lower in latitude. And they have to do that for the protection of their citizens, their customers, and also their flight crew. What I did hear is that, on an average flight, say between here and I don't know about India, that's farther, but between here and maybe Europe, I would be exposed to radiation from galactic cosmic rays that might be equal to a chest X-ray. So we don't want to have many of those either. So, but I fly a lot, so I'm not glowing yet. So I guess it's still okay. And hopefully, what I worry about is, we're now talking about. In fact, there was a ship that left yesterday, taking people farther out. We want to go towards the moon. We want to go to other planets.
Yes.
How can we protect those people? I'm not quite sure. I'm not quite sure our vehicle can be built strong enough with a strong enough protection to protect them. There is a capsule in the ISS where all the residents go and sit during a major magnetic storm. What happens on an aircraft traveling to the moon? Hopefully someone's working on that. It's not me.
Thank you.
Thank you for your question.
Thank you.
Thank you. Anybody else has a question?
Yes. Can I ask a question?
Yeah. Can you please switch on your? Yes. Thank you, Dr. Banerjee. Please. Just 1 second. Patricia, could you please stop sharing your screen so that we get to see? Great.
Yes.
Yes, Dr. Banerjee, please go ahead.
Yes. Professor Patricia Doherty, I first congratulate you for your excellent, informative, and illustrative presentation. I have one question is that same I'm worried about that what Anand Krishnan the solar sphere that is being predicted in the newspapers, the net. My question related to that, whether the occurrence of the solar flare and CME, is there any correlation of simultaneous occurrence? And second thing is that, is there any probability that in the equatorial anomaly area where these effects is more stronger and more damaging?
So it was a little bit of interference, but I think I heard some of your question. Where is it more strong and damaging? Certainly a geomagnetic storm is going to hit, it can hit globally, but in places like mid-latitudes, we get gradients that we don't usually see, like those storm enhanced densities. That's what we see during a major magnetic storm. Certainly, and they can affect around the world. Very often, for scintillation and plasma bubbles, if we get a strong magnetic storm, scintillation is suppressed. And it's suppressed primarily because we get a reduced pre-reversal enhancement of the electric field. And that then, pushes the plasma down further so that we don't then see those scintillation effects. However, that's not 100% the time. Very often we do see an enhancement in scintillation. I'd say more often you see a suppression in scintillation, but often you see an enhancement of scintillation. And I think what you mentioned and what Dr. Anand had also asked is, I also see those, you see a newscast, the world ends tomorrow. There's going to be a Carrington event and, everything's going to shut down. We're going to go back to the Stone Age. Don't read those. Or, hopefully we never go there. I think it's, that's just, news of the day, scare tactics. However, it's not full scare tactic because we as scientists know that these storms can happen and things are going to result from these storms. But that's what we're all working toward, is trying to, first of all, watch those storms, predict where they're going, predict what the result will be, and be planning to mitigate what's going to happen before it gets to us. And model prediction. Forecast is still, a high interest in our research field, is how do we forecast these solar events. But with the increased monitoring of the sun, I think we'll get there. But I really don't like seeing those news articles of the world is going to end tomorrow because there's a solar storm coming. I get my phone rings off the hook at that point in time. Everybody calls me from the Boston area. Is this really going to happen? So, and I don't know.
Agree.
I don't think so.
Agree with you.
Okay, so I'd like to now take a question from our YouTube viewers. This question has come on the chat box, and it says, this is from Srijan Panja. Does solar storm affect the global warming as it produces lots of cosmic rays that helps nucleation and eventually causes shielding of sunlight? Do you have any comments?
Yeah, it really doesn't appear to cause an immediate or direct effect in the troposphere. Okay, we see most of the effects of the space weather in the magnetosphere and the ionosphere. Certainly, the sun has an effect on temperature of the Earth, but it mostly comes in the brightness of the solar radiance. I think we can all agree that the prime cause of climate change is greenhouse gases. We see volcanoes, we see El Nino causing more of the effects of climate change. I don't see a clear link between a solar storm and climate change. I don't think it warms the Earth. It does cause other problems, as we've just seen, but I don't believe there's a connection.
So in terms of energy, there's not enough energy that could be dissipated in the Earth's atmosphere to warm it up significantly.
I heard somewhere, I read somewhere that the difference in how from solar minimum to solar maximum, you might see like a 0.1% increase in the temperature of the Earth due to just that change. And so I can't make a clear connection between just going from solar max to solar min, or even from a solar eruption to climate change. I don't see that evidence. And maybe it's a thing for us to continue to study, but I don't see it. I think bigger problems we have to fix first. Emission control, certainly greenhouse gases is something that if we can control a lot of that, I think, climate change will certainly take a turn in the right direction.
Great. So I have another very interesting question which has come on the chat box from Raka Dabade. It says, you mentioned about a capsule used on International Space Station for protection. What is it possibly made out of?
Oh yeah, I would have no idea, except that it's resistance to it's a resistant capsule to radiation. I don't have the details of what it is, but
is it very thick material?
I have no idea. But I do know that during the storms of 2003, the space station came in direct contact with those solar storms, those Halloween storms, and the astronauts inside were located it's an aft portion of the ISS where they can go, and they are protected from radiation. However, keep in mind, some of these things can happen pretty quickly. Those radiation can move fast. So, hopefully we can see them coming and they can get everyone to safety before it would actually hit. And I think certainly it did.
Okay, so there was another question on the chat box. Well, now we had another question on the chat box, but I think it's already answered. It said, what would be the connection, if any, with the Earth's atmospheric conditions and the storms that we experience? I think the person meant solar storms. if is there a connection between the atmospheric conditions and solar storms?
Not really. Not really. Most of the effect of these solar storms is in the magnetosphere and the ionosphere. Okay, tropospheric effects are minimal, if any. So I don't see that. It does. So yeah, we get a major magnetic storm. Does it change the weather on Earth? No. It's going to rain, or it's going to be sunny. It's going to snow. It'll be whatever it was going to be.
Okay.
And if there is an effect, it's a minor effect.
Okay. So may I now request those of you who are logged in to our panel, any questions from the panel here? I think Dr. Watts had a question. Oh, Professor Krishnan. Okay.
Can I ask a question?
Animesh, please go ahead.
Okay, thanks, Patricia, for your nice talk. You mentioned that in 2006, December perhaps, but there was a major event which disrupted the GNSS communication, GNSS system, navigational system. So do you think that there is a real danger if in any future strong solar event that may disrupt navigational system, those are based on GNSS satellites, and that may cause a major disaster? For example, say Air Force air landing system, aircraft landing systems are now much dependent on GNSS system, as you mentioned. So could there be a real danger that this kind of major solar event can disrupt GNSS-based navigational system? That could be a real holding point.
Yeah. Sorry, go ahead.
And is there any mitigation strategy in place that is how to mitigate that kind of effect or that kind of disruption in GNSS-based system?
So a GNSS-based system such as WASS, such as GAGAN,
yes,
they are very, very strong. They are built to. They're looking at the ionosphere all the time. They're making measurements all the time. If there's anything that shows any kind of a gradient, okay, it changes the availability of the system. In other words, the system is not to be used for civil aviation during those times. So the maps that I had showing, the maps of over the North American continent under a nominal condition where we had full availability, and then we had storms that showed that we lost availability mostly over Alaska or Canada during most of those storms. The WASS system did what it was supposed to do. It realized that things were unstable, that there was a gradient in the area, and basically we couldn't rely on the system to give us a truly accurate position. So basically the system became unavailable for use. And that GAGAN is based on the same principle. So the systems are very robust. They would not transmit hazardously misleading information saying, you can land, here's your runway, but actually your runway is over there. That's not going to happen. They are very robust. The only thing that happens is you lose availability. You cannot use the system during a time when we cannot count on the integrity of the measurements that we see. So no, that's not going to happen. Many studies that are done by GAGAN and other systems. What could happen is, if there's a major storm, our satellites are, can be affected. We saw that in one of our slides as well. I'm not aware of any effects of even the major storms of 2003 on the GPS satellites. They were all up and running in 2003 where we had those big storms. I'm not aware that the systems failed. Those GNSS satellites failed. So they must be built in a different way, and they weren't affected. We do need to continue to watch what happens in the future.
Okay, thank you. That answers the question. Thank you very much.
I have a very interesting question on the panel, but before that, I think I will take up one question from the YouTube chat box. It says from Poonam Arora, says, are there permanent stations to measure the 11-year solar cycle? How does it affect the life on Earth? Are there permanent stations to measure the 11-year solar cycle?
Yeah, I think there are many places around the world that are measuring sunspots. I mean, you can measure, you can watch sunspots yourself with a small telescope, but I can't name one, but certainly I think SWIPS, you know, the NOAA system is watching them. Belgium is watching them. I'm sure it's somewhere in India they're watching the sunspots. They are there for our watching, and I think they're simple enough to see. So I think they're done. What was the other half of that question?
Well, the other half said, how does it affect life on the Earth? It probably doesn't affect life on the Earth too much.
No, the sunspots don't affect life on Earth, but certainly the major solar eruptive events that we talked about, those CMEs, solar flares, they can affect our technological systems, and those affect us. There's also, you know, many studies out there on how is it affecting us biologically. If you have, you know, radiation effects, you know, these major CMEs, are they affecting us biologically? I got a question one time saying that, you know, very often, you know, there's this idea that a full moon will change people's personalities, or, you know, will induce a woman to give birth during a full moon. Does space weather have anything similar? It is a focus of study in some groups. I'm not involved with those studies, but I'm very interested to see if they define some sort of biological relationship to solar activity. I mean, not solar activity itself, but to space weather events. I'm not aware of it just yet, but I think people are working on it.
Great. So I think I have a very interesting question on the panel here. It says, do you see a key role for a new out of ecliptic mission for space weather monitoring as opposed to an ecliptic mission? This is from Dr. Srikumar.
Could you repeat the question? I'm not sure I understand the question.
Do you see, I think perhaps in your talk, you did mention a space mission for weather, for monitoring a space mission, which was an ecliptic, which was in the ecliptic plane. So he says, do you see a key role for a new out of ecliptic mission for space?
I think that certainly would be interesting. I don't know that there is something developed just yet on that topic, but it certainly is an interesting thing to think about. So I just became, as you mentioned, introducing me, the working part-time for NASA, the Helios Physics Division, as the chair of their Space Weather Advisory Committee. I'll bring it up in our next committee meeting just to see where they are with their plans for some of those satellites.
Yeah, basically what he is asking is whether you will have another Ulysses-like mission, which means he has to do a gravitational swing and go to the high ecliptic of the sun and study it in the same manner.
That would be a great
expensive mission.
Yeah, that would be that would be an expensive mission. But yes, I think that I'll investigate that further, but I don't believe that there's anything planned just yet.
Yeah.
Right. So I don't see any more questions, but given the large number of questions and comments that followed your talk, I'm sure, well, there is one more question. I'm sorry. Dr. Hariom Watts, please go ahead.
This decreasing solar maximas, the solar maximum values are decreasing in this cycle and previous cycle, and if it happens, is this a worry?
Is it a worry? From where I sit, studying space weather effects, I'm glad it's going to be smaller this time around. We're not ready for the Mother Nature to unleash herself on us just yet. But is it a worry that it would continue? I think, we've had small solar cycles before. There were 100 years ago. There was also long, long ago the Maunder minimum, where they saw an increase in the ice cap. If it happens again, it's nature. I don't think there's anything that it would be a worry about. I'm more worried about what happens if we have a major solar storm at the moment, and are we ready for it? So, but is there a worry about, will it decrease even further? I don't know.
Okay.
Thank you.
Thank you. So, well, I think finally we are coming to the end of this program. And thank you very much, Dr. Patricia Doherty, for that wonderful lecture. And going by the number of questions and the amount of discussion that followed, I think all of you will agree with me that this has been a wonderful talk, and it's been really topical and very, very interesting theme. So thank you once again. So now I will request my colleague, Mr. N.K. Wadhwa, to propose a formal vote of thanks. Mr. Wadhwa. I think you have to unmute yourself, please.
Okay. Thank you, Dr. Gupta ji. Dignitaries, Dr. Patricia Doherty, Professor Venugopal Achanta ji, Director CSIR-NPL, Dr. S. Anantakrishnan ji, President Indian Radio Science Society, Dr. Amita Sen Gupta ji, Chairman AP Mitra Memorial Lecture Committee, Shri R.P. Saxena, Convener AP Mitra Memorial Lecture Committee, family members of late Dr. AP Mitra, NPL Former Scientists, Forum colleagues, NPL fraternity, distinguished participants from Indian Radio Science Society InRaSS, ladies and gentlemen. I feel honored and privileged to get an opportunity to propose a vote of thanks on this historic occasion of 7th AP Mitra Memorial Lecture today on World Ozone Day. We are extremely grateful to Dr. Patricia Doherty, Director and Principal Scientist, Institute of Scientific Research, Boston College, USA, for having accepted our request to deliver the 7th AP Mitra Memorial Lecture. Ma'am, we are all enlightened with your lecture on storms from the sun, the science of space weather. Our grateful thanks to Professor Dr. Venugopal Achanta ji, Director CSIR-NPL, for presiding over this function and gracing this event with his encouraging welcome address. My deep regard and thanks to Shri R.B. Saxena ji, Convener AP Mitra Memorial Lecture Committee and Secretary of NPL Former Scientists Forum, who has always been a source of great encouragement and inspiration to the organizing committee. We convey our gratitude to Dr. Anantakrishnan, President InRaSS, and an eminent radio astronomer who has always been very supportive and mentor to Radio Science Society. Special thanks are due to InRaSS and CSIR-NPL for jointly organizing this prestigious lecture. We are grateful to entire team of InRaSS for successfully organizing this event. I would like to take this opportunity to place on record my heartiest thanks to Dr. Amitabh Sen Gupta, Chairman AP Mitra Memorial Lecture Committee, for perfect logistic support and guidance he has always extended to organizing committee of AP Mitra Memorial Lecture. Now, special mention, we have with us today the family members of late Dr. AP Mitra ji, who have graced this occasion by their presence. Since the initiation of AP Mitra Memorial Lecture Series, the family has been associated with NPL Former Scientists Forum and have made donation towards this cause. The forum is extremely grateful to them. And at the end, I convey our thanks to all distinguished delegates on the dais, and persons who are attending through YouTube, invitees, and my NPL-FSF senior officials, Dr. R.G. Sharma ji, Dr. J.C. Sharma ji, Dr. Vikram Kumar ji, Dr. Kishan Lal ji, Dr. S.C. Garg ji, Dr. V.N. Bindal ji, and all in the audience who have patiently attended this lecture. This reflects their respect and regard to late Dr. A.P. Mitra ji. Thank you all. Over to Dr. Sen Gupta ji.
Thank you very much, Vadvaji,
Thank you.
for that formal vote of thanks. So once again, thanking Dr. Patricia Doherty for kindly agreeing to give the talk, and thank everyone for attending and making a very live question, answer, and comments and discussions. So now I'm pleased to close the session. Thank you all once again. Good night.
And,
Well,
and thank you for honoring me with the invitation to give this lecture. I feel
thank
much
you very
closer,
much.
closer
Thank
to my
you.
esteemed colleagues now. Thank you.
Thank you.
Thank you.
All right. I now close the meeting.